Gypsel wind turbine capstone project. Team members Jake Towarnicki, Ethan Huber, Pablo Franco Almonte, and Jeffrey Jackman. And now for a brief introduction. Jibs have been used on sailboats for years and have been proven to increase the lift generated from the sails, allowing the sailboats to travel a lot faster than if they didn't have a jib sail. If a similar type of modification can be made on the blades of wind turbines, there could be increases in energy captured from the wind, which in turn increases energy output. During the summer of 2019, research on thin airfoils and the jib concept was done, which demonstrated a close to 40% increase in lift generated by the pair of thin airfoils. Then, in the following summer of 2020, a conceptual testbed for the thin airfoils was designed for the purpose of testing different sail configurations. And so the scope of this capstone project is to redesign the mechanism and build a scale model of the proposed wind turbine, along with electrical systems for reading wind speed and controlling the parameters of the wind turbine. This is for the purpose of proving that the concept works and to redesign if any problems are encountered. The model will be used as a testbed for tuning the turbine blades' orientation and sail tension while it is being driven by the wind. The turbine will focus on generating torque at low rotations per minute. The data collected in tuning will be used as a starting point for the operation of the 2-scale wind turbine.
The main mechanical system for this design uses a one-dimensional swash plate driven by 2 servos to rotate both masts while inside the hub assembly. This design allows for the masts to be adjusted while the entire hub assembly rotates around the center shaft. Here's a photo of the center shaft after it was done being machined. There is a through pin hole for the hub and then a slot for the grooved carrier. This slot allows us to slide the grooved carrier along the shaft while still transmitting torque through it. This is a video showing the machining process of the center shaft. The material for this shaft ended up being very hard, so the process of machining the slots and the through holes ended up taking a lot more time than expected. This is a video showing the facing of the bearing adapters. These adapters allow us to mount a circular bearing into the center of the extruded square aluminum tubes. Shown here are some photos of the center body assembled after we got the grooved carrier follower machined and the holes drilled for the main body. The servos in this photo are just stuck to the main body using double-sided tape. This was used to show linear motion of the grooved carrier follower while the servos were actuating it. Here's a video from some of our preliminary testing showing the grooved carrier follower actuating along the center body. Shown here is a photo of our chain drive system. This system uses a sprocket on the center shaft of the turbine to spin a motor. The motor will ultimately be used for capturing energy, but for testing we'll be using this to measure the energy potential of the system.
We will now discuss the electrical systems and coding that are part of the jib sail turbine system. After our electronic parts were received, we made sure that each component functioned properly when connected to power. This included uploading generic codes to the Arduino Mega microcontroller board and attaching the 4 servo motors to power them up and test their range of motion and strength capabilities. In the same testing run for part validation, we also tested the Adafruit anemometer. We discovered that when running all 4 motors at the same time, the 5-volt power supply we were using, shown on the right side of the image here, was not powerful enough to supply the power for all 4 motors at the same time. Because of this, we changed the power supply to come from the 12-volt power cord that came with the anemometer and go through 2 LM7805 voltage regulators run in parallel. This allows the motors to draw power separately from the Arduino board, which will be powering the LCD display, screens, and the anemometer separately from the motors. After we knew our electronic components were functioning properly, we began to plan out how each of the components would be connected and coded into the microcontroller. The wiring diagram displayed here shows each of the components connected to the breadboard and the microcontroller. We are using 2 LCD display screens to display the system information with 4 user inputs via 2 potentiometers and 2 buttons. Each of the potentiometers will control one of the sets of servo motors to adjust the sails. When adjustments are made, the LCD screen will display the position of the arm of the servo motor that adjusts the pitch and whether the sail is being pulled in or out by the continuous servos, which will tighten or loosen the sail, acting as a winch. The anemometer will tell the wind speed that the turbine is seeing when it is out in the field, which will be used to determine whether the wind speed has exceeded the safety limit set by the system. After assembly of the system is completed and all electronic components have been wired and coded correctly, we will begin to test the outputs from the turbine. We will be able to measure the angle that the sail's pitch can be adjusted to and the amount of tension adjustment that can be made via the winch motor, as well as the voltage output from the DC motor. Ultimately, getting a voltage out of the DC motor at the back end of the system will determine the turbine's success.
If the project proves to be successful, composite wind turbine blades have the potential of being replaced by a jib and mainsail, also known as fabric-thin airfoils. This in turn will simplify maintenance and logistics associated with the transportation of the wind turbine components. Since a sail uses a simple mast with rope to hold it in place, it does not need to be transported in one piece. It can be disassembled for transportation and assembled on site. The fabric of the blades can also be folded for transportation. This significantly reduces the amount of trips and trucking equipment required to get the turbine on site. Future goals. Future goals include designing a rotating nacelle mechanism for orienting the wind turbine to the direction of the wind. This mechanism will need to mount onto a 33-foot water pump tower. Also, the mast, boom, and sails will need to be made for the prototype before testing can begin. Calibration and optimization will need to be made for the wind turbine. The optimal rotation speed will need to be determined, and the angle of attack and tension of the sails for the incoming wind will also need to be determined. Once optimization is complete, we ultimately want to measure the power output from the 24-volt DC motor while the turbine is being spun by the wind. The voltage output will tell us if it is feasible to build a full-scale prototype. And finally, I'd like to acknowledge Mr. Timothy Sichler, who is the project sponsor and an assistant teaching professor at Penn State Wilkes-Barre, and Dr. Rangan Nathan, professor and program chair of mechanical engineering at Penn State Berks.